So the talk today is heat and fluids in the crust. It's different from many of the other talks in the meeting so far in a couple of ways. Number one, my field area is the entire planet. And number two, I'm going to present all of my results on the back of an envelope, or as you think you'd say in German, auf dem Bierdeckel, right? So the field area is the whole planet, and the picture shows you that we live on a blue planet. So it's not surprising that one of the main features I want to talk about comes from the world's oceans. And what I often say is that the geothermal gift to Geosciences is an explanation for seafloor spreading, which is in fact a geothermal process whereby magma comes up from the mid-ocean ridge. Sorry. Here in the picture on the right, so you have an initial temperature, a hot temperature, but once it sees the surface, then you get cooling through times 1, 2, 3, and 4, etc. And that has some consequences. The changing geothermal gradient at the surface gives rise to a changing heat flow. The cooling multiplied by a thermal expansion coefficient leads to subsidence of the seafloor. And then if you follow this path down here, identifying the lithosphere, then you can pack out the base of the lithosphere, or the LAB. Now formally this is known as Kelvin's problem, because Kelvin said if the Earth starts in a heated state like this, then each one of these curves represents a time of cooling. So if we measure the thermal gradient at the Earth's surface, we can determine the age of the Earth, which he did in 1864 and came up with 100 million years, right? And that's a history of science. The formal solution to the one-dimensional diffusion equation with no heat sources is this. It simply says the rate of change of temperature at any time is proportional to the curvature in the temperature profile. So where you have curvature, then you get cooling and so forth. A solution for that is known as the air function solution, which is really nice and simple. It only has two variables, or three variables: the initial temperature, the thermal diffusivity, and time. To remind you what the air function looks like, I've put it down at the bottom left-hand side. It's very simple. The properties are the air function of 0 is 0, air function of small x is x, and the air function of a large number is 1. So we ask the question, what's a large number? And the answer is that the air function of 1 is 0.86, the air function of 2 is 0.998, and so everything happens between basically 0 and 1 of this, which is the square root of 4 alpha t, which we call the thermal length. So for t equal 1 million years, and the thermal diffusivity of 32 kilometers squared per million years, this turns out to be 10 kilometers. For 100 million years, it's about 100 kilometers. So for the ocean evolution, everything takes place in about 100 million years, which is almost the age of the oceans that you have. So let's calculate three things. Let's take the gradient of this and multiply it by thermal conductivity to get heat flow. If you collect the constants and group them together, then heat flow turns out to be 500 over the square root of the age of the seafloor. If the age is in millions of years, this turns out to be milliwatts per square meter. So for 1 million-year-old seafloor, we have 500 over 1, which is 500 milliwatts per square meter. If this is 100 million years, this goes down to 50 milliwatts per square meter. So this is the heat flow on the seafloor. If you track bathymetry between the initial state and some state and multiply by this an expansion coefficient and add in the isostatic loading for seawater, you get bathymetry is 2.7 plus 1/3 the square root of age. So when age is 0, that's the depth of water on a mid-ocean ridge. And when t is 81 million years, to make the square root 9, and 9 over 3 is 3. So this makes it 5.7. That's the abyssal plain. And then finally, if you track the lithosphere thickness, it's simply 11 square root of time. So at 1 million years, this is 11 kilometers. At 100 million years, it's 110 kilometers. That's the ocean. This is our gift as geothermal scientists to the world, or to geoscience. So for 3/4 of the Earth's surface, or 70% of the Earth's surface, here we have in 3 simple little back-of-the-envelope calculations, we have the heat flow, we have the bathymetry, and we have the lithospheric thickness for 3/4 of the Earth's surface. So we should be out on the side of the streets waving flags saying this is our gift to geophysics. Well, maybe not waving our flags until we see if the data support it. So I want to show you the data, and I'll go in reverse order from the bottom up to the top. So here's a plot of LAB depth versus the age of the seafloor, 0 to 160 million years. Here's the prediction, and there's the data coming principally from surface wave dispersion, from tomography, and more recently from, what's it called, the S to P conversion. What's the terminology? Receiver functions, thank you. So pretty good, okay? Pretty good. Bathymetry, very good. So here's the prediction. This is bathymetry down to 6 kilometers. Here's the age of the seafloor again. The dots are binned 1 million year seafloor. The gray area is 1 standard deviation. So a noisy record, but the prediction is really very good. And finally, heat flow. Not so good, not so good. So it fits out here, fits out here, but it absolutely does not fit here. So you could say, let's throw out the theory because it doesn't fit, but the bathymetry is so good, and this depends on the integrated temperature difference down to the base of the lithosphere, whereas the heat flow is simply a surface measurement over 3 or 4 meters with a oceanic heat flow probe. So we keep the theory, and we propose the statement here that if you don't get what you're looking for, maybe something else, something more interesting is going on in this region of young seafloor. So very early on, people such as Clive Lister, Earl Davis, some people at Woods Hole said, maybe what's happening here is in the young seafloor, seawater is going into the crust and mining the heat. And the water is coming out in topographic highs where we can't measure it, and the water's going in sediment ponds where we go and measure it. So everywhere you want to measure it in very young seafloor, you get a heat deficiency. Well, this is just an invitation for me to ask the question, how much water is going through the Earth's crust? So this is a fun little game. What I've said is that in this picture, back one. So in this picture of the heat flow versus age, this is the deficiency that I think is mined by water. The area under the curve here that's shaded is watts per square meter times time, so it's joules per square meter. So I'm equating so many joules per square meter from the ocean crust into heating a column of water of height h. So I'm putting water into the crust, bringing it out, and equating that water to this area over here. You solve algebraically for h. It's simply that area divided by density, specific heat, and delta T. If you plug in reasonable numbers, then what you get for h is 200 kilometers. 200 kilometers of water. So that's the average ocean depth is 4 kilometers. That's 50 ocean depths. So it works out really nice as 50 ocean depths in how long? 50 million years. So that means the whole ocean is going through the crust every million years. Amazing. Okay. So our picture of how this is working now has evolved on a seafloor where you have ocean crest here with unsedimented region, and then you get more and more sediment over time. So we think there's open exchange of seawater here. There's leakage here, and it's only when you get well sedimented crust, or if the driving force convection gets less, and that apparently takes place at about 50 million years. Now, there are some spectacular pictures of this. If we go to a ridge, this is a picture that when I was at the Canberra IUGG in 1971, Dick Holland from Harvard University came out and showed this, and they'd gone down in a submersible and take this picture for the first time. So it's the first picture of black and white smokers, and not only is there this plume of mineralized fluid that comes out, precipitates and makes these chimneys, but there's a biotic community of clams and tube worms and so forth around it that's fascinating. So my question is, how much heat is coming out? So we'll go back to an envelope, and if we have fluid coming out of a pipe, then the amount of energy is just equal to mc times delta T. The power you divide by time, so all we need to know is the mass flow. They measured in that submarine, they measured a temperature of 350 degrees C, a velocity by a film of about 3 meters per second of the stuff coming out, and the radius of this tube is about 1/10 of a meter. If you plug those numbers in, this little black smoker is 130 megawatts. So I'm sorry, Ilmo, about your... But one of the consequences, if you're pulling 130 megawatts of heat out of this smoker region, or this vent region, it can't last very long, right? You just cool it off. And indeed, when people went back 10 years later, these communities were dead and the smokers weren't smoking anymore. So that's the picture of black smokers. So back to the seafloor, where we're able to make measurements is out here when we've had sediment in sediment ponds. So I was fortunate to go out with Roy Heinemann and Earl Davis out of Pacific Geoscience Centre and make some heat flow measurements. But I wanted to just make a comment on how technology and technology changes are really important. So the first time I went out to do heat flow measurements, we were using what's called a Bullard probe. So it's just basically a single probe with thermistors in it, and you let it go into the sediment in the sea floor. But you had an impossible engineering demand because the probe had to be as small as possible to have a short time constant, but as strong as possible. So that's an incompatible set of things. So the probe would go in, the ship would move around, and then when you pulled out, the probe bent. So making a heat flow measurement was winching down for 2 or 3 hours in 4 kilometers of water, putting it into the bottom for half an hour, winching it back up to see if it was bent, because if it was bent, it wouldn't go in the next time, taking the measurement, and then going down again. So you'd be lucky to get 2 measurements in a day. And if you only got 2 measurements in a day and maybe just 1, then you wanted to go some distance away for another measurement because you didn't want to spend the time repeating the measurement. So that's why up through the 70s, measurements were spaced far apart. But 3 things happened in the 70s. Number 1, GPS positioning came along, so ships knew where they were to a few meters rather than hundreds of meters. Secondly, microcomputers. The first Intel chip was 1974. And then Clive Lister, an irascible genius, invented what he called the Lister heat flow probe, which was the violin bow. So for the first time, he said, thinking about a violin where you've got the bow, which is the strength member, and then the string, which is the sensitivity. And he said, why don't we put that in a heat flow probe? So here's the strength member. It's actually 2-inch drill string. And then all the thermistors are in this 1 centimeter, very fast response thing. So this was allowed, it would never bend. So you put it in the seafloor. And after about half an hour, you had your measurement. You pulled it out of the seafloor. And then you move the ship maybe 100 or 200 meters, put it down again, and then down again. So you could do 15 measurements in a day. And it was in operational in what they call pogo mode. Any of you remember what a pogo stick is? You know, you jump ahead and so so that's what was available. The way that the data stream looks, and you had microcomputers that could store gigabytes of data. So it could go down for a day, and you can make 15 or so measurements in a day. So the data stream looks like this. So the probe goes into the seafloor. All the different thermistors warm up, and you get a temperature. Then you fire a heat pulse, and as the heat pulse decays, you get thermal conductivity from the decay. So that gives you a conductivity versus depth. Put them together in a Bullard plot of thermal resistance versus temperature, and the slope gives you heat flow in milliwatts per square meter. Beautiful. Not my work, still beautiful. Okay, so this is one of our measurements on the Wanda Fuca Ridge. So what we've got here is the seafloor image with single channel. Let's go back one, sorry. Yeah, so this is the seafloor image. So this is the basaltic basement, and there's the sediment, so 0 to 25 kilometers. And here's 2 days of measurements. So there's 17 measurements here one day. Here's 17 or 18 measurements the next day. And what we get is a beautiful set. The black dots are raw data. The open circles are sediment corrected data. They're basically the same. The dashed line is the expected heat flow for a little younger than 4 million year old seafloor. So the values basically agree, except you get some deficiencies, and then you get these peaks. So this peak is leakage through the sediments of hot water coming up to the surface. This measurement of about 2 watts per square meter is this venting of hot water through that little seamount on the seafloor. I call this the no guts, no glory point, because if you drop this instrument on basalt, you might destroy it. So what we wanted to do is get as close as this as possible and make this measurement. So we said, let her fly, and in fact, we got a good penetration in this. So this is measurements, detailed measurements in a place where the wavelength of what's going on here is the wavelength of the topography, which is a few kilometers. Yeah. Okay. So the last thing I want to do is just pure enjoyment. So it comes from a suggestion by John Verhoeven back in 1980, in which he said you could calculate the energy release in all of these Earth processes. So earthquakes, volcanoes, metamorphism, etc. The basic physics is trivial, it's high school physics, and the rules are we'll calculate the power in watts, we'll use powers of 10, and no quibbling in doing any of this. So let's go through this. It's really quite simple and it's great fun. So seismic energy is based on the elastic rebound theory. So you build up a strain in a region, then you release the strain in the earthquake, and the seismologists give us a relationship with the energy and the magnitude ms of the earthquake. So if you put that in for a magnitude 8 earthquake, you generate 10 to the 16 joules. If we want to turn that into watts, you have to know how many magnitude 8s you have in a year in 3 times 10 to the 7 seconds. Put that in, and it turns out the magnitude 8s generate about 2 times 10 to the 9th watts. Now you have to add up all the magnitude 7s, 6s, 5s, and so forth. But when you do that, you get for about a hundredth of a terawatt. So seismic energy release, if you add in slow earthquakes, rock breaking, etc., 0.02 terawatts. Volcanism is pretty easy. Volcanoes expend energy by blasting rock up into the air. So here's MGH for the cloud of volcanic dust. Divide by time, so all you need to know is the height of the cloud and how much volcanic dust you put up in a unit of time. That's what volcanologists do for us. They produce catalogs of these numbers, and it turns out that that's also about 0.02 terawatts. But there's also the volcanoes put magma on the Earth's surface. At a mid-ocean ridge is the biggest volcanic process, and you can punch in those numbers. They're a little bit higher, so volcanism is 0.2 terawatts. Metamorphism, that's an endothermic reaction. So it takes 50 calories or 0.2 megajoules per kilogram of rock that you metamorphose. So all you have to do is say, where are the metamorphic factories? And they're in accretionary prisms, and they're in continental collision zones. And if you put the numbers in here, you also get about 0.02 terawatts. Mountain building is a little more complicated, because what you're doing is you're raising rock up through this, you're raising the potential energy, mgh, power divided by time. So this is just the mass of the mountain area times g times the uplift rate. And reasonable numbers put in, you need the mass, which you can get, or the uplift rate from these, and erosion rates will give you uplift rates, and mountain building is about 0.4 terawatts. So we're getting bigger, but not very big. Meteorites, when meteorites come in, they give up 1/2 mv squared when they hit the Earth. But people who study bolides give us this kind of a curve or plot of a log-log plot of the size of stuff coming in versus the time between the impacts. So really small stuff like a millimeter come in every 30 seconds, but the big ones, 10 kilometers, come in every 10 million years. But if you integrate over this curve, you get that right now, meteorites don't give up very much energy. Earlier in Earth history, they gave up a lot. And then finally, heat flow. And this is really nice because this is something we measure. We don't have to estimate. I think you know this number between oceans and continents, and it turns out to be 44 terawatts. So putting these into a table infuriates my geological colleagues, but makes me very proud that heat flow dominates this. And somebody showed a slide earlier that said heat flow is basically a heat engine. So heat is driving convection, it's driving tectonics, and it's best to think of these other things as just the exhaust for our heat engine in the world. Now there's two things that are missing here. Two things that are missing. They're humans and they're solar. So let's just quickly go through that. So humans, we're now approaching, we're approaching 8 billion people. Just think, we consume 2,000 calories per day. Here in the hotel, probably more than 2,000 calories. If you take, that's food calories, a food calorie is a kilocalorie. So if you put that together and divide by the number of seconds in a year, it comes out to 100 watts. So all of us are 100-watt generators. That's why it's hot in an elevator or in a room. But if you put that together for 100, let's go back one. Can we go back one? So if you put that together, but that's just basically to survive. We get 100 watts times 8 billion people, but we produce energy and we consume energy. And when you do all of that, humans are about 15 terawatts consumption of production of energy. And then solar is the big one. So we have a nuclear power plant in the sun, but when you get solar energy at 1 Earth distance, it's about 1,000 watts per square meter. That's the solar constant. And if you take it, how much is intercepted by the world, it's 170,000 terawatts. So putting those back in the table, what we have is these two additions, and we certainly get a justification for using the term Anthropocene. It was introduced because we're now changing the atmospheric temperature, we're changing the atmospheric chemistry, we're changing the oceanic chemistry. So here's another way in which we're competing with geological processes as an agent of geological change. And then the fact that solar is so much more means that our future not in every case, but is going to be tied to future. So we've covered a lot of ground. I'm sorry, I'm taking. This is me logging a borehole in central Utah. I've got my gear measuring a borehole right here. You sit out in the wild like this, you have a lot of time. It takes about half a day to monitor a 200-meter well at 1 meter interval. So it's a lot of time to think about Earth and fluids on the Earth's crust, and especially to work things out on the back of the envelope. So thank you.